Hi, welcome to chapter 9. In this chapter, we are going to be looking at covalent bonding and molecules. In the previous chapters, we did look at the periodic table, we did look at the elements, and we look at the types of bonding. We talked about ionic bonding, which was the bonding between metals and non-metals, and we talked of covalent bonding, which was between the non-metal elements. So we will be looking at covalent molecules, and covalent molecules are molecules that are formed between non-metals, and the bond that is formed between non-metals is called a covalent bond. So covalent bonds is formed from two atoms by sharing of electrons, and these atoms are non-metal atoms. So why do elements bond? Why do atoms bond together? They bond together in order to attain an octet. And the octet rule states that atoms are stabilized by having 8 electrons in the valence shell. So this is true for most elements, but in the course of this lecture, we are going to see some exceptions. Not all the elements actually go by the octet rule. So in chapter 5, we did look at the Lewis symbols, and we are going to be using the Lewis symbols here in this chapter to draw the Lewis structures. So if we look at an element like chlorine, we have 2 chlorine atoms to form a molecule of chlorine. Each chlorine atom has 7 valence electrons. One thing that you have to know is that in this chapter we will be talking only of the valence electrons. So one chlorine atom has 7 valence electrons. For it to attain an octet, they will need to share each of their electrons. So if they share this one and this one, it means that all of them are going to have 8 electrons. Now, the 2 electrons, this one and this other one, they are going to combine, and that gives us this now. So these 2 atoms, they have attained the octet. So if you see 2 electrons or you see a line, so a line or a dash represents 2 electrons. You can call this a bond, a single bond. It represents 2 electrons. So the Lewis structures show the arrangement of covalently bonded atoms, and we use a dash to represent 2 shared electrons. So what you actually see here, this is the Lewis structure, and it shows the arrangement of covalently bonded atoms. So this is the Lewis structure of water, and this is the Lewis structure of carbon dioxide. We are going to show how to draw the Lewis structure, and you will see all the bonds and the lone pairs involved in that structure. Now let's look at covalent double and triple bonds. What I just showed you here, this is a covalent single bond. Okay, we are going to see the situation where we have a double and a triple bond. In the case of the double bonds, we are going to use atoms like oxygen. We know that the oxygen atom has 6 valence electrons, which means that for the oxygen atoms to have an octet, each of them is going to bring 2 of the electrons. So this atom is going to bring 2. This other atom is going to bring 2 of its electrons. So they are going to share all of those, and that is going to form 2 bonds. Remember, 2 electrons is a bond, and then the 2 of these other electrons is a bond. So that's what you see here. So that forms a double bond. And you see that each of these atoms have attained an octet. So each bond is 2 electrons, and they are counted for both of the atoms. So these 2 bonds are counted for this atom, and these 2 bonds are also counted for these atoms when you are counting the number of electrons for the octet. Now you see that here we have 1, 2, 3, 4, and 4 for the 2 bonds. That makes 8. Now let's look at the case of the covalent triple bonds. An example of an element that we are going to be using here is nitrogen. We know that nitrogen has 5 valence electrons, and for the 5 valence electrons, each nitrogen atom is going to bring its 3, and they are going to combine to have 8. So for this nitrogen atom, it's going to bring 1, 2, 3. This other nitrogen atom is going to bring 1, 2, 3. So they're going to share, and the 6 electrons is going to give us 3 bonds. Remember, each of them still have this lone pair. and that is what you see here. So this lone pair, the 3 bonds, this lone pair, which is directly equivalent to this. So this is a triple bond, this is a double bond, and that is how they are being formed. So let's look at the pairs of electrons in compounds. Here in this chlorine molecule, we are going to see that there is what we call the bond pair and there is what we call the lone pair. So what is the bond pair and what is the lone pair? This line or this dash is a pair of covalently bonded electrons. So you are talking about a bond pair. And this lone pair of electrons on the chlorine atom, we call them a lone pair of electrons. So each of these chlorine atoms have three lone pairs. This has 3 lone pairs. This other one has 3 lone pairs. And each of them have 1 bond pair. Now, in most molecules, atoms follow the octet rule as we've already stated. So we are going to see that carbon dioxide here, this is the Lewis structure. So we are going to see how to draw the Lewis structures. For carbon dioxide here, the carbon atom has attained an octet. So each of these is 2 electrons. When you count 1, 2, 3, 4. So that is 2 times 4, that makes 8. So the carbon has attained an octet. Now for the oxygen atom here, we have 2 lone pairs which have 1, 2, 3, 4 electrons plus 2 bonds which have 4 electrons. So 4 plus 4 makes 8. Same for this oxygen atom. Now we see that for the water molecule here, the oxygen atom has an octet, 2 pairs and 2 lone pairs, that makes 8. And for hydrogen, hydrogen has a duet. So most of the elements don't attain an octet, but for hydrogen, it is what we call a duet. So hydrogen has needs just 2 electrons, and it is satisfied. We are going to see the exceptions to the octet rule shortly. So now let's see what we call the exceptions to the octet rule. And for the exceptions to the octet rule, we are going to outline a number of things here. So the first thing that we are going to outline is an incomplete octet. When we talk of an incomplete octet, that is a situation where an element or an atom has less than 8 electrons, but it is satisfied. For example, we have boron trifluoride here. For boron trifluoride, the central atom here is boron. It has just 6 electrons and it is satisfied. Another example that we can think of is beryllium chloride. So for beryllium chloride, it will have a structure where beryllium is the central atom and the 2 chlorines are this way. So this is what you will have for beryllium chloride. You see that it doesn't have an octet. So this is another exception to the octet rule for beryllium chloride. Now, for the elements in the periodic table, the elements that are found from the 3rd row. In the 3rd row here, we are looking at phosphorus, sulfur, chlorine, argon, selenium, bromine, krypton, iodine, xenon, and radon. All of these, they have what we call an expanded octet, which means that they will actually have more than 8 electrons for the central atom. So the central atom will have more than 8 electrons. In that case, we call it an expanded octet. We are going to see an example of phosphorus trichloride and phosphorus pentachloride. For phosphorus trichloride here, we see that phosphorus here has an octet because it has 1, 2, 3 bonds which are 6 electrons plus this lone pair that makes 8. So it has an octet. Now that's for PCl3, phosphorus trichloride. For phosphorus pentachloride here, we see that phosphorus has 10 electrons. This is 1, 2, 3, 4, 5. 5 bonds, and each bond is 2 electrons, so that makes 10. So why do these elements have an expanded octet? As we have seen in the previous chapters, there is a D subshell that is empty, and that is for phosphorus, and phosphorus can actually accept electrons into the empty D subshell. That is what makes it to have an expanded octet. So this is the complete octet for phosphorus trichloride, and this is the expanded octet, that is phosphorus pentachloride. Now let's now see how we can draw Lewis structures. First thing, make sure you understand how to draw the Lewis structures, because the part that follows, we are going to be talking about the shapes of the molecules. They stem from the Lewis structure. So make sure you understand how to draw the Lewis structure. So what is a Lewis structure? A Lewis structure shows you how the bonds and the electrons, that is the bonds and the lone pairs, are arranged in a molecule. How do we draw the Lewis structures? There are a number of rules that we must follow. The very first rule is that, one, we have to add up all the valence electrons in the molecule that we are talking about. The second rule will be that we have to draw the frame, we have to frame the structure. Now, talking about the valence electrons, we have mentioned this a couple of times. Let me just remind you how to get the number of valence electrons for each atom. So for the group 1A, they have 1 valence electron in the outermost shell. So for the group 2A, they have 2 valence electrons. For the group 3A, they have 3 valence electrons. For the group 4A, 4 valence electrons. Group 5A, 5 valence electrons. So if you have a molecule like carbon dioxide, if you want to calculate the number of valence electrons, carbon is found in group 4. So you will have 4 electrons. Plus for oxygen, oxygen is found in group 6, and there are 2 of them. So we have 2 times 6. That makes the number of valence electrons. So you have 4 plus 12. That makes 16 for the number of valence electrons. So for Lewis structures, we are going to be dealing only with the valence electrons. Now, what is the third rule? The third rule states that we have to fill octets on outer atoms first. So there is what is called a central atom, and the other atoms are called the outer atoms. Shortly, I will show you how to decide which atom is the central atom. Now, the fourth rule is that you have to fill the octet on the central atom. And after filling the octet, we may fill it by taking the remaining electrons. After filling the octet for the outer atoms, the remaining electrons, we put them on the central atom. And we could also make the central atom to have an octet by using double or triple bonds if need be. Now, let's look at an example here. Draw the Lewis structures, the Lewis structure for nitrogen trichloride, NCl3. So the first thing, we know how to write the formula of nitrogen trichloride because we've looked at that. The second thing now is we know the number of valence electrons in each of these atoms. Okay, so for nitrogen, nitrogen is found in group 5A, so it will have 5 valence electrons. Chlorine is found in group 7A, so you have 7 valence electrons, and we have 3 of them. So that will be 7 times 3. Now, we have to sum up the valence electrons and see what we get. If you sum 5 plus 21, that gives you 26 valence electrons. That is rule number 1, sum electrons. So we've calculated the valence electrons. Rule number 2 states that we should draw the framework. For us to draw the framework, there has to be a central atom and the other atoms. Now, which one is the central atom? So the central atom will always be the atom that is found to the left. In this case, we are looking at nitrogen and chlorine. Nitrogen and chlorine. So nitrogen here is found to the left and chlorine is found to the right. So the central atom will always be the one to the left and below. So here, nitrogen is the central atom. So let's draw our framework. So we have nitrogen at the center and the chlorine atoms are linked to the nitrogen atom by bonds, single bonds first. Now we have to count. We've said a single bond is equivalent to 2 electrons, which means that in this framework, we've used 2 times 3. That gives 6 electrons. Now, Rule number 3 says we should fill octets on outer atoms. The outer atoms here are chlorine, chlorine, chlorine. And we have 2 electrons. So to fill the octet, we are going to add 6 electrons on each chlorine atom. 6 electrons is equivalent to 3 lone pairs. So let's start. Right. So we filled the octet for the outer atoms. So if you count for each of these chlorines, you have 1, 2, 3, 4, 5, 6, 7, and 8, because a bond is 2 electrons. So there is an octet here, there is an octet here, there is an octet here. So let's count how many electrons have we used all together. Have we used the 26 valence electrons that we have? So we have 6 for these 3 bonds, and each of these chlorine atoms have 6. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So we've used 24 out of the 26 valence electrons. So the other rule states that we should fill the remaining electrons on the central atom. So we have 2 more. So the 2 more electrons, we are going to place them on nitrogen. So that is it here. And now let's see if all of them have an octet. Nitrogen has 1, 2, 3 times 2, that is 6, plus 2, that makes 8. So that is the correct Lewis structure for nitrogen trichloride. Now let's draw the Lewis structure again for formaldehyde. Formaldehyde is commonly used to manufacture plastics, and we are going to see how we can draw the structure of formaldehyde here. So first thing, we are going to calculate the number of valence electrons. Carbon is found in group 4, 4 valence electrons. Hydrogen has 1, so 1 valence electron times 2. And oxygen is found in group 6A, 6 valence electrons. So we have 4 plus 1 times 2 plus 6. So if you sum that up, you are going to obtain 12 valence electrons. Now, which one is going to be the central atom? One thing that you must remember is that hydrogen can never be the central atom, because hydrogen can only form 1 bond. Okay, so here hydrogen can never be the central atom. In no case will you ever see hydrogen being the central atom for the Lewis structure. Now we are now going to decide between carbon and oxygen which of them has to be the central atom. So we've said the one that is found to the left is the central atom. Carbon here is found to the left and oxygen to the right. So our central atom is carbon. So we are going to now draw the framework. Carbon at the center, 2 hydrogens and 1 oxygen. So that is what we have. Now, what you have to understand now is that hydrogen has already attained its duet. So any other electrons that are left are going to be filled on the oxygen. And if there are any left, we then put them on the central atom. So we've used 6 electrons here. 3 bonds is equivalent to 6 electrons. So we have 6 more electrons. So all the 6 electrons, we are going to put them on the oxygen atom, which is the outer atom here. So there we are going to put the 6 on the oxygen. Now, let's see if all the elements or the atoms have attained the octet. Hydrogen is okay. This other hydrogen is okay. This oxygen is okay because it has 8. 1, 2, 3, 4, 5, 6, 7, 8. This carbon is not okay because carbon only has 6. So the last rule states that we can complete the octet of the central atom by converting double bonds or triple bonds if need be. So in this case, you will see that if we convert one of these bonds, carbon is going to have 4 bonds, that is 8 electrons, and the octet will be complete, and oxygen as well will be complete. So we are going to convert this bond, this lone pair, to a bond, and that makes it now easy. So carbon here now has attained an octet, oxygen has an octet, and the hydrogens have an octet. So let's look at molecules and charge. So one thing that you have to know is that the charge is very important, and we will see how the charge comes about. So for polyatomic ions, we know that there are groups of atoms that have an overall charge. we have all of these here. We have the ammonium ion, this is a polyatomic ion, we have the hydroxide, we have the nitrate, we have the nitrite, we have the sulfate, the phosphate, the carbonate, and the acetate. All of these are polyatomic ions. And what you see here, the charges, you see a positive here, you see a negative here, you see a positive and negative. That is what is called formal charge. So formal charges are a method of identifying charged sites. So how do you identify the charged site? That is done through a method that is called formal charges. I'm going to show you how to calculate the formal charge. You will be able to assign formal charges to atoms in a Lewis structure. So for the formal charge, one electron from each bond is assigned to one atom. So for this bond, if we want to calculate the formal charge, the one of the electrons will be assigned to this atom and one of the electrons will be assigned to this other atom. So that is how we do with the formal charge. There is a formula how to calculate formal charge. The formula to calculating the formal charge states that formal charge is equivalent to number of valence electrons in a neutral atom minus the number of covalent bonds minus the number of unshared electrons. As an example here, we have the hydroxide ion. Let's see how we are going to calculate the formal charge on each of these atoms. Let's start with the hydrogen. The formula for formal charge states that is the valence electrons in the neutral atom minus the number of covalent bonds minus the number of unshared electrons. Hydrogen has one electron in its neutral atom. So in this hydroxide ion here, the number of bonds for hydrogen is 1. So we are going to have 1 because hydrogen has just one valence electron. So number of valence electrons is 1 minus number of covalent bonds. Hydrogen here has just 1 minus number of unshared electrons. Hydrogen has no unshared electrons, so minus 0. So that gives us 1 minus 1 minus 0, that is equal to 0. So hydrogen has no charge. Now let's look at the oxygen atom. To calculate the formal charge, we have valence electrons in neutral atom. Oxygen has 6 valence electrons in the neutral atom minus number of covalent bonds. Here we have just one covalent bond minus the number of unshared electrons. Here we have 1, 2, 3, 4, 5, 6 unshared electrons. So 6 minus 1 is 5, minus 6 is minus 1. So that is the charge, and the overall charge of this molecule is minus 1. So that is where the minus comes in. Now let's look at the formal charge for oxygen and nitrogen atoms. The oxygen and nitrogen atoms often have formal charges. Let's look at the example here for water. We are going to take the water molecule and we are going to take the deuterium here, which is heavy water. So we see that for water, the formal charge on the oxygen is 0, and the formal charge on the oxygen here for this hydronium ion here is plus 1. Now how do we get plus 1? If you calculate the formal charge here, let's finish with this one. Here is 0, here is minus, and here is positive. We just did that for the hydroxide ion and we saw that it was negative. So we have already treated this case. For this one, the formal charge is going to be 0. So let's calculate it here. We said formal charge is the number of electrons in the neutral atom minus the number of bonds minus the number of unshared electrons. So oxygen has 6 valence electrons minus number of bonds. We have 2 bonds. That is 6 minus 2. And we have 4 unshared electrons. 6 minus 2 minus 4. That gives 0. So the oxygen here has 0. The formal charge on the oxygen is 0. Now let's look at the formal charge on this oxygen atom here. We have 6 minus bonds. The number of bonds that we have are 3. So we have 6 minus 3. And then the number of unshared electrons are 2. So 6 minus 3 minus 2, that gives us 1. So that is why you see plus. That is the charge here. So that is how you determine the formal charge. Now for the nitrogen atoms here, we can calculate the formal charge here, here, and here. So let's start here with the one that is negative. How do you get negative? For nitrogen, nitrogen has 5 valence electrons. So we have 5. So we calculate the formal charge just for the central atom here. That is what we are doing, because hydrogen is already 0. We've already seen that hydrogen is 0. So here nitrogen is the number of valence electrons for the neutral atom is 5, minus bonds we have 2, minus unshared electrons we have 4. 5 minus 2 is 3, minus 4 is minus 1. So we have minus. Here for this nitrogen in the compound here in the middle, we have 5 minus 3 for the bonds, minus 2 for the unshared electrons, that gives 0. Here in this last structure, we have 5 valence electrons minus 4, which are the bonds. We have just 4 bonds, that gives us plus 1. So we have positive. Now, automotive airbags contain sodium azide, which has a formula Na(N)3. The Lewis structure for the azide ion without charges is shown. So you should be able to draw the Lewis structure for this azide. We've already seen that. Calculate the formal charge on each atom in this structure. Next question. What is the overall charge of the azide ion? So the overall charge is the sum of all the charges. Now, let's look at the nitrogen in the center here. We know that nitrogen has 5 valence electrons, and we have been given this structure which has 4 bonds. So 5 minus 4, and we have no unshared electron. So that's 5 minus 4 minus 0. That gives us 1. So plus 1. So the central atom here has an overall charge of plus 1. The next thing, let's look at this other nitrogen. The nitrogen atom here, it has 5 valence electrons. There are 2 bonds, so 5 minus 2. There are 4 unshared electrons, 5 minus 2 minus 4. So that gives us minus 1. Same thing, let's look at the last nitrogen atom here. 5 valence electrons minus 2 minus 4, that is minus 1. Now, to know the overall charge of the atom, of the molecule here, we are going to add the charges. That is minus 1 plus 1 minus 1. So that gives us minus 1. So here we have minus, here we have plus, here we have minus. So the azide ion is going to have an overall charge of minus. So that is how we get the minus. The minus here is obtained from minus 1 plus 1 minus 1. Now let's see how we can draw the Lewis structures for polyatomic ions. So for polyatomic ions, we are going to follow exactly the same thing that we were doing, but we are going to add or subtract electrons based on the charge on the ion. So we are going to follow the similar rules that we have been using for neutral molecules, and then we are going to consider the charge when finding the number of valence electrons. Remember, we said for anions, for polyatomic anions, when there is a negative, it means that the species has gained electrons, and when there is a positive, it means that the species has lost electrons. So when we see an ion that is negative, it means that we are going to add electrons. So how many valence electrons are in a hydroxide ion? So the hydroxide ion is OH minus. So if we have to calculate the number of valence electrons, let's start. Oxygen has 6 valence electrons. Hydrogen has 1 valence electron. And the charge here is negative, which means that it has gained an electron. So we have plus 1 here. So the valence electrons are 6 plus 1 plus 1, that is 8. That is how we get the number of valence electrons in a polyatomic ion. So you can as well calculate the number of valence electrons in PO4 3 minus. In SO4, 2 minus. In CO3, 2 minus. So calculate the number of valence electrons in each of these compounds, and then you can draw the Lewis structures after. So let's draw the Lewis structure for the nitride ion. So the nitride ion here, and we are asked to show all the non-zero formal charges. So we are going to start by writing the formula, which is here NO2 minus. We sum the valence electrons. Nitrogen has 5, oxygen has 6 times 2, plus the negative here, which means plus 1 electron. So if we sum all of those, we have 18 valence electrons. Next, we draw the framework. For the framework here, the central atom is going to be nitrogen, because we have nitrogen and oxygen. Nitrogen is to the left. So the central atom is nitrogen, connected to 2 oxygen atoms. The third, we fill the octets on the outer atoms. So we've used 4 electrons for the 2 bonds, so we are left with 14. So we fill the octet for this oxygen atom. So each of these oxygen atoms is going to take up 6 to attain that octet. So we fill 6 for each oxygen atom, and we count the number of valence electrons in this structure. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have 2 electrons more. Where do we place the 2? On the central atom. So 2 electrons on nitrogen. Now, do all the atoms have an octet? Oxygen here has an octet, oxygen here has an octet, but nitrogen here has just 6 electrons. 1, 2, 3, 4, 5, 6. So nitrogen doesn't have an octet. So we are going to convert one of the lone pairs here. If you convert it on this oxygen or on this other oxygen, it's going to be the same. So we are just going to convert one of the lone pairs to make a double bond here. Right. So that gives us the complete structure for nitride ion. Now we've been asked to show the non-zero formal charges. So we have to calculate the formal charges of all these atoms. So for this atom, we have 6. Oxygen is 6. It has 6 valence electrons with a neutral, minus number of bonds 1, minus unshared electrons minus 6. So 6 minus 1 minus 6 is minus. Here for nitrogen, nitrogen has 5 valence electrons, minus number of bonds minus 3, minus unshared electrons 2. So that gives us 0. So for this minus 1, this is 0. For this other oxygen atom, oxygen has 6 valence electrons, minus number of bonds, which is 2, minus unshared electrons 4. That is 0. So for the non-zero, you have to show the non-zero. This is the only one that is non-zero. Now let's see how we can identify the best Lewis structure. So there are molecules that actually have more than one Lewis structure. In that case, which one can we conclude that is the correct structure? We are going to use an example of phosgen here, which is a very toxic chemical that was used in World War I. So we have the structure here, the framework. We've already calculated the number of valence electrons. We have the framework, and we are given these structures. So these are the 2 structures. So now, question, which of them is correct? Now I'm going to tell you something. The structure that is correct, when we use formal charges, we use the one that has the lowest formal charge, or the one that the formal charges are zeros everywhere. So the one that has formal charges of 0 everywhere, or the one that has the lowest formal charge, is the best structure. So in this case, if you calculate the formal charge for this chlorine, the formal charge is 0. So we have 7. If you have 7, chlorine has 7 valence electrons. 7 minus 1, which is the number of bonds, is 6. 6 minus 6, which is unshared electrons, that is 0. So same thing here, 0. Carbon has 4. 4 minus 4 bonds minus 0 on shared, that is 0. For oxygen here, oxygen has 6 minus 2, that makes 4 minus 4, that is 0. Now, if you calculate the formal charge here, you will see that chlorine here will have, so we have everything here 0. Okay, zeros everywhere. Formal charge 0, 0, 0, 0, 0, 0, 0 everywhere. And if you calculate the formal charge here, you will see that chlorine here will be positive and oxygen here will be negative. So the most stable is the one that has formal charges of 0 everywhere. So this is the correct structure. This is not the correct one. Now let's look at what we call resonance structures. There are some molecules that actually gives you the possibility to have more than one structure, and each of those structures are correct. Okay, let's look at the example here of the nitride that we already saw. So this double bond can be this way, or the double bond can be this way. So all of these structures are correct. So this is what they are called resonance structures. So whenever you see the double-headed arrow, it shows the resonance structure. So if we decided that we were going to choose this as the correct structure, that will mean that the nitrogen-oxygen bond will be longer than the nitrogen-oxygen double bond. Okay, so experiments have shown that the nitrogen-oxygen bonds are actually the same. So the structure is not this one, the structure is not this one. So the correct structure is a structure that is in between the two. So the double bond here is actually delocalized over the whole structure. That is why you see it here, and it is localized, delocalized. So the negative here is not on this oxygen atom or on this oxygen atom. So the negative is shared on the both oxygen atoms. So that is, you see the negative half here and negative 1/2 here. Now, the resonance structures are a set of structures that show how electrons are distributed, and we have to use the resonance structures when a single Lewis structure is insufficient, like we already saw for the nitride ion. So a single Lewis structure is insufficient. You cannot determine if this is the correct structure or this. So the correct structure is in between. When you see this arrow, immediately think of resonance. Now let's look at ions with resonance structures spread charges. With resonance structures, we will see that they spread charges over multiple atoms. So the charge will be spread over the multiple atoms. Now for the nitrate, we will see that the charge will be spread over the whole structure, and you often see us write it like that. When you see like this negative, when you draw the Lewis structure, if you draw the Lewis structure, you're going to have something like the oxygen atoms will be here. This is not just the correct structure, I'm just trying to show you what happens. You are going to put it this way. So that indicates that the electron, that the charge here is spread over multiple atoms. So here we have the Lewis structure for the phosphate. For the phosphate, you will see that if you count the number of valence electrons, so what I will ask you to do is to pause here and draw the Lewis structure for the phosphate. Start by counting the valence electrons, deciding which is the central atom, and make sure each of them have the octet. Now, if you do that, you will see that to complete the octet for the phosphorus here, one of these bonds is converted here. You see that in the next structure we are going to convert but this other one. In the next we'll convert this other one, next this one. So you see here, these are the resonance structures. We have the double bond at the top, here we have the double bond at the side, here we have the double bond at this other side, and here we have the double bond at this other side. That is to say that only second bonds and lone pairs are changed in resonance structures. Here we've changed just the second bond and the lone pair. So that is the resonance structure, and the charge is spread over the atoms. Now The nitrate ion has three major resonance structures. Draw each structure, and based on these structures, what is the average charge on each oxygen atom? So we drew that for the nitrate, and we said the charge on each oxygen atom was -1/2. So now we have to draw for the nitrate. So this is the Lewis structure for the nitrate, where the double bond is at this position. We could draw this Lewis structure, and we decide to shift the double bond to this direction and to this direction as well. So we are going to have three possibilities. So we have it here, the double bond and the lone pairs, and this one. We have the second scenario here, and we have the third scenario here. Now the double-headed arrow shows that there are resonance structures. Now we've been asked, draw each structure. We've drawn the structures. Based on these structures, what is the average charge on each oxygen atom? So we've calculated the formal charges here. The formal charge for this oxygen here is 6 minus 1 minus 6. That gives you -1. For the nitrogen here is 5 minus 4 minus 0. That gives you 1. For the oxygen here is 6 minus 1 minus 6. That gives you -1. And here is 0. 6 minus 2 minus 4, that's 0. So same thing, you calculate here, that's the same thing. You will see that each oxygen here actually has a charge of -2. So -2, -1, -1. Here that gives you like -2. Here you have -1, -1, that is -2. So here is 2 negative. So this oxygen is negative, this one 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 is negative. So you have 2 minus signs. So the average charge on each oxygen atom, since the correct structure will be a delocalized structure, the actual average will be -2/3, because we have 1, 2, 3 of them, and we have -2 on each. So the average is going to be -2/3. Now let's look at the shapes of molecules. So when we breathe, we know that we breathe out carbon dioxide and water vapor. Now all of them are gases and water is liquid. So why is carbon dioxide a gas and water a liquid? Okay, when we look at the shapes of the molecules and the polarity, you will be able to say why why carbon dioxide is gas and water is liquid, because of the structure, shape of the molecule. And we are also going to look at the polarity. Now let's see how we can predict the shapes of molecules. For us to be able to predict the shapes of molecules, we have to start by drawing the Lewis structure. So whatever we'll be doing here, we are assuming that you already know how to draw the Lewis structure. So if you cannot draw the Lewis structure for any element or for any compound, make sure you go back and practice it before you continue with the shapes. So we are going to use a method that is called the valence shell electron pair repulsion theory, or simply VESPA. So VESPA stands for valence shell electron pair repulsion. So there is a repulsion that exists between electron pairs, and that repulsion brings about the shape of the molecules. The lone pair repulsion is always greater than the lone pair bond pair, which is in turn greater than the bond pair. Now, looking at carbon dioxide here, we are looking at the central atom. So for us to determine the shape of a molecule, we are looking at the central atom, and we are going to be counting the number of electron pairs or electron groups. So we are going to be counting the number of electron sets or electron groups. So this carbon has 2 electron groups. A lone pair or a double bond or a triple bond or a single bond is considered as 1 electron group. So this is 1 electron group. So this is 1 electron group, and this is another electron group. So carbon dioxide, carbon here has 2 electron groups. For carbon here in methane, carbon here has 4 electron groups. 1, 2, 3, 4 bonds, 4 electron groups. Here it has 1, 2 electron groups. Here for the nitrite, the nitrogen here has 3 electron groups. The lone pair is an electron group, the double bond is an electron group, and the single bond is an electron group. So how can we predict the shapes? Now there is what we call the molecular geometry, and there is what we call the electron geometry. So for the electron geometry, we are going to count all the arrangement of the electrons around the central atom. So we are going to count the number of groups around the central atom. So the number of groups here, we have 1, 2, 3, 4. We have 4 groups around this oxygen. So that gives the electron geometry. So the electron geometry is considering everything, the lone pairs and the bonds. Now, for the molecular geometry only considers the shape based on the arrangement of atoms. It doesn't consider the lone pairs. So you will see that this molecule, the molecular geometry, will be different from the electron geometry. At times you may have the electron geometry to be the same, but that is not always the case. Now let's look at the case where we have 2 electron sets or 2 electron groups. When that happens, when we have just 2 electron groups, remember I've talked about electron pair repulsion. The electrons will always try to repel themselves as much as possible. So in the case of 2 electron sets, they will be far apart as much as possible. And when that happens, the electrons will arrange themselves to be 180 degrees apart. So that is the farthest they can be for the 2 groups. So here we have the electron geometry to be linear. We have 2 electron groups, we have 2 groups, and the molecular geometry to be linear as well, because we have just 2 atoms. Remember, the molecular geometry only considers the atoms that are bonded. Now, I've said double and triple bonds count as 1 set. If you have this triple bond, it's 1 set. You have a lone pair, it's 1 set. If you have a double bond or a single bond, it's 1 set. Now, we are looking at geometric stability. Which geometry is most stable here? We are looking at the central atom. For the central atom, we have 2 electron sets. So which one is most stable? Will it be this one, or this one, or this one? For you to answer that question, remember we've said the electrons repel themselves and we want to be farthest apart as much as possible. So the correct structure here is C, because they're 180 degrees apart. Now, in each of them, there are 2 sets of electrons, so the shape is linear. And this is what you get from here. Now, let's look at a case where we have 3 electron sets. When we have 3 electron sets, the shape is trigonal planar, because all the bonds or the lone pairs are on the same plane. Now, let's look at an example here. We already saw this compound, formaldehyde. So from the Lewis structure, we see that we have 3 sets. For the 3 sets, that makes it trigonal planar, and the electrons want to be as far apart as possible. That will give you a bond angle of 120 degrees, 120 degrees here and 120 degrees here. So for the linear, we said the bond angle was 180 degrees. So for the trigonal planar, it's 120 degrees. So the electron geometry here, the electronic geometry is trigonal planar. 1, 2, 3, trigonal planar. And the molecular geometry as well is 1, 2, 3. We have 3 bonds, 3 atoms bonded. So that is going to be trigonal planar as well for the molecular geometry. Now let's see another example here. We are looking at the electronic geometry. We are looking at the nitrite ion here. For the nitrite ion, from the Lewis structure, we see that we have 3 electron sets here. For the 3 electron sets, that gives us a trigonal planar electronic geometry. Okay, now what about the molecular geometry? We've said for the molecular geometry, we consider only the atoms that are bonded. Here, this is a lone pair, so it is not going to be considered for the molecular geometry. So we know that the lone pair here will repel the bond pairs, and the shape of the nitride ion here is going to be bent. Same thing for water. We'll see that when we're talking about 4 electron sets. So let's look at 4 electron sets here, and the shape is going to be tetrahedral. So normally when you have 4 electron sets, you have tetrahedral. You may think that if we have 4 electron sets, we are actually going to have like an X. So if we have an X, that means in an X, the bond angles are 90 degrees apart. So the bond angles in an X shape here, they are 90 degrees apart. However, if we rotate 2 of the bonds, we create more space. So if we rotate 2 of these bonds, we'll create more space. So that gives us what is called a tetrahedron. So in a regular tetrahedron, the bond angle between 2 of the bonds is 109.5 degrees. Remember, the electrons want to be as far away from each other as possible. So that will adopt a tetrahedral shape. So the tetrahedron is like 2 V shapes in planes that are perpendicular to each other. Now, let's look at the example here for methane. So methane, if we draw the Lewis structure, this is what we obtain. And if we are calculating the electronic geometry, it will be tetrahedral because we have no lone pairs, and molecular geometry will be tetrahedral as well. Now for ammonia here, if you draw the Lewis structure, this is what you obtain. For the electronic geometry, we have 4 groups, that is tetrahedral. For the molecular geometry, we have just 3 bonds. The atoms say that, so that is going to give us a trigonal pyramidal shape. So we've seen 4 groups where the molecular geometry is tetrahedral. We've seen 4 groups where the molecular geometry is trigonal pyramidal. Now we are seeing 4 groups here, and the molecular geometry will be bent. This is water. So if you draw the Lewis structure for the water molecule, this is what you get. Now the electronic geometry, we have 4 different sets of electrons. So 4 each time when we have 4 different sets is tetrahedral. So the electronic geometry is tetrahedral and the molecular geometry is bent because we are considering only the bonds between the atoms. Now this is a recapitulation. If we have 2 electron sets, the electron geometry is linear. So this is an example of the model. In this case, all the sets are bonding sets and we have no lone pairs. So the molecular geometry will be linear as well. An example that we saw was carbon dioxide. Now, if we have 3 electron sets, the electron geometry is going to be trigonal planar. And this is the model. So we could have 3 bonding sets and no lone pair. In that case, the shape of the molecule is trigonal planar. But we could also have 2 bonding pairs and 1 lone pair. In that case, the shape of the molecule is bent. An example that we've seen is the nitride ion. Now we can also have electron sets as 4. So when we have 4 electron sets, the electronic geometry is tetrahedral. Now the model here, this is the regular tetrahedron, and for the 4, we may have 4 bonding sets, or we may have 3 bonding sets, or 2. So if we have 4 bonding sets, there are no lone pairs, and the shape will be tetrahedral. An example is methane. Now if we have 4 electron sets and 3 bonding and 1 lone pairs, the molecular geometry is going to be trigonal pyramidal. Example, ammonia. If we have 2 bonding sets and 2 lone pairs, we are going to have a bent shape. An example is water. Now, let's look at the electronic and molecular geometry for a compound that has more than 1 central atom. So we are looking at this compound here. with more than one central atom, how then are we going to determine the shape? So we are going to determine the shape of each central atom here. So for this carbon, we are going to determine the shape for this carbon, and for this oxygen and this carbon. Now, the electron geometry for this carbon, we have three groups, three sets here, 1, 2, 3. That is trigonal planar. So everything in green here will have a trigonal planar. So for this carbon is 1, 2, 3 trigonal planar. For this other carbon is 1, 2, 3 trigonal planar. Now for this oxygen, how many electron sets do we have? We have 1, 2, 3, 4. So that is tetrahedral. And for this other carbon, we have 1, 2, 3, 4. That is tetrahedral. So that is the electronic geometry. If you were to talk about the molecular geometry, in this case, you cannot say because we have more than one central atom. Now, lithium carbonate is a simple ionic compound that is widely used to treat bipolar disorder. What is the molecular geometry of the carbonate ion? So to determine the molecular geometry, you must first of all draw the Lewis structure of the carbonate ion. So this is the carbonate ion is CO3 2 minus. So you calculate the number of valence electrons. Carbon is 4, oxygen is 6 times 3, that is 18 plus 4, that is 22 plus 2, that makes 24. So you draw the Lewis structure and determine the formal charge. What is the molecular geometry of the carbonate ion? So for you to determine the geometry, you must first draw the Lewis structure. Now, for the carbonate ion here, we see that we have 1, 2, 3 electron sets. So when we have 3 electron sets, what do we have? And we have 3 electron sets and no lone pair. So that is a trigonal planar. So the electron geometry is trigonal planar. Now, what about the molecular geometry? The molecular geometry is trigonal planar as well, because we have 3 bonds. Now, let's look at what we call polar bonds and molecules. So, when we looked at the bonding, we said the atoms share electrons to attain an octet. Now, one thing that you have to realize is that that electron that is shared is not equally shared between the atoms. At times it could be equally shared, at times one of the atoms will pull the electron more to itself. When that happens, we'll be talking about electronegativity. So, if we look at hydrogen fluoride here, the bond here is fluorine will be more electronegative and it will pull the body electron more to itself. In that case, it will become partially negative and hydrogen will become partially positive. So this is how we indicate a polar bond. Or we could still indicate it this way. The arrow is pointing towards the more electronegative atom. So, what is electronegativity? Electronegativity shows how strongly atoms pull bonded electrons to themselves. And here, when you look at this periodic table, you see the electronegativity values here. For lithium is 1, for beryllium is 1.5, for boron is 2, for carbon is 2.5, for nitrogen is 3, for oxygen is 3.5, for fluorine is 4. So what do you notice here? You see that the electronegativity increases across the periods from left to right. Now, let's look at the period. Let's look at the group. For group 7, 7A, the periodic, the electronegativity for astatine has 2.2, iodine has 2.5, bromine has 2.8, chlorine has 3.0, fluorine has 4.0. You see that they are increasing from bottom to top. Now, we see that the iodine is 2.5, bromine is 2.8, and so that is how they are increasing. So fluorine is the most electronegative atom in the periodic table. So that means that if you have a bond that is formed between chlorine and fluorine, chlorine will pull the bonded electron more to itself. Fluorine will pull it because it has a higher electronegativity than chlorine, and when it pulls it, it will become partially negative. Now let's look at the metals here, fluorine and cesium. So francium and cesium. Francium has an electronegativity value of 0.7 and cesium 0.7. So you see it increases up. So the least electronegative atom in the periodic table, we are talking about fluorine, francium and cesium. Now let's see how we can compare covalent, polar covalent and ionic bonds. So we looked at ionic bonds and we said an ionic bond is formed in an ionic compound where there is a complete transfer of electron from the metal to the non-metal. So this is the ionic bond. For a covalent bond, we said the covalent bond is formed by sharing electrons. And if the electrons are equally shared, it is a simple covalent bond. But if any of the atoms is more electronegative, it will form a polar covalent bond. So like example, we already saw HF. Now, how do we determine if a molecule is simple covalent, polar covalent, or ionic? So when you calculate the electronegativity difference between two atoms, for example, here we have fluorine and fluorine, that is 4.0 minus 4.0, that is 0. So when the electronegativity difference is less than 0.5, the compound is simple covalent. When the electronegativity difference is between 0.5 to 2, the compound is polar covalent. And when the electronegativity difference is more than 2, the compound is ionic. We will see an example. So let's look at the analogy here for the polar covalent bonds. We see two dogs here. This is a bigger dog and this is a smaller dog. And the two dogs are pulling a rope. This rope that they are pulling, the bigger dog has more ability to retain the rope. And if they are pulled apart, the rope will stay with the bigger dog. That is the same thing like for hydrogen fluoride. You see the fluorine is more electronegative and it will have the bonding electron to itself. So which bond is more polar, a carbon-oxygen bond or a fluorine-sulfur bond? Show the direction of polarity for both bonds. So we are going to use the table of electronegativity here to calculate the electronegativity values. So the first one is the carbon-oxygen bond. The carbon has 2.5 and oxygen has 3.5. So the difference between two of them is 3.5 minus 2.5. So that gives us 1. Now let's look at the fluorine-sulfur bond. Fluorine has electronegativity value of 4. So this, and sulfur has an electronegativity value of 2.5. So the difference is 1.5, which means that it is polar covalent, because we've said less than 0.5 is just covalent, between 0.5 to 2 is polar covalent, and 2 and above is ionic. Now we've been asked which bond is more polar. So since the difference between the fluorine and the sulfur is 1.5, it is more polar because it has a bigger value, 1.5 and 1. So this one is more polar. Now the next question, show the direction of polarity for both bonds. Now to show the direction of polarity, we've said the more electronegative atom will always have the partial negative charge. So if we are using the partial positive and the partial negative for the fluorine oxygen, or for the fluorine sulfur or the carbon oxygen, we will see that for the carbon oxygen, oxygen has an electronegativity value of 3.5, so it will be partially negative. And for the fluorine sulfur, fluorine has a higher electronegativity value, so we draw the arrow pointing towards the more electronegative. So if you want to use partial negative and partial positive here for carbon and oxygen, we'll demonstrate that it will be moving towards that here for carbon oxygen will have the minus because it is more electronegative, and fluorine here the minus because it's more electronegative. So now let's look at the molecules with dipoles. So molecular dipole is also called net dipole or simply dipole. And what is the dipole? Dipole is an overall polarity in a molecule. So we were looking at the polarity here. So we have looked at these polarities. So when there is an overall polarity in a molecule, that leads to what is called a dipole. So we see the water molecule here. The water molecule is polar covalent because of the shape and because of the arrangement of the atoms. So the characteristics here are determined by the shape and the way the atoms are arranged. Now let's look at how we can identify a net dipole in a molecule. Here for water molecule, we know that oxygen is more electronegative than hydrogen, so the arrow will move towards oxygen in both bonds. So there is going to be a net dipole in water because everything is moving towards oxygen. So there's a net dipole. Now let's look at carbon dioxide. The carbon-oxygen bond, as we just saw, is polar. Okay, the electronegativity difference is 1. So for the carbon-oxygen bond, here it will be 1, and here it will be 1. Now, because of the shape of this molecule, the molecule is symmetrical. This one will be pulling it this way, and this one will be pulling it this way. So this cancels out the effect, and this molecule now becomes not net polar. So there is no net dipole here. So we are going to use an analogy here. So if you have a molecule of sulfur dioxide, this is the Lewis structure, is it going to have a net dipole or not? Remember, we just saw carbon dioxide here and it doesn't have a net dipole. What affected it? The shape of the molecule, and if there are any lone pairs. Here there were no lone pairs, and now here in sulfur dioxide there is a lone pair here on sulfur. Okay, so there is a net dipole here. So the analogy is that if you have two tractors that try to pull this trunk here, this tractor will be pulling this way and this other tractor will be pulling this way. The net dipole, the pulling effect, is going to move the log this way because the tractors are pulling with the same strength. So the net effect will be felt here. Now identify which of these have a net dipole. Methane is non-polar. The carbon-hydrogen bond is non-polar. So we are not going to talk about this. So there are no polar bonds. For boron trichloride here, so we know that all of these bonds are polar. The chlorine bromine, the chlorine boron, look at the chlorine here, chlorine is 3, boron is 2. That means the net electronegative difference is 3 minus 2, which is 1. So everything will be pointing towards chlorine from boron. Now, the boron-chlorine bond is polar. But one thing that you should know, they pull equally the same. They pull the same. This one pulls the same, this one pulls the same, this one pulls the same. That makes it to be net, not polar. So there is no net polar ability here, so there is no net dipole. What about difluoromethane? Difluoromethane, let's see the Lewis structure. For difluoromethane, let's look at hydrogen chlorine. Hydrogen is 2.1, carbon is 2.5. The difference is 0.4. So the carbon-hydrogen bond is not polar. Now let's look at the carbon-fluorine bond. Carbon is 2.5, fluorine is 4. So that makes a difference of 1.5. So here we have carbon-fluorine. Because fluorine is more polar, is more electronegative, the arrow will be pointing towards fluorine, and for the two of them. So they are polar bonds. Because there is no symmetry in this molecule, there is no symmetry here, it makes it to have a net dipole. So now, how dipoles affect the properties? When we started, I was talking of breathing carbon dioxide and water. So why is carbon dioxide a gas and water a liquid? So we see that carbon dioxide is linear and there is no net dipole. There is no net dipole in carbon dioxide, so the atoms are free. But for water, water has a bend shape and there is a net dipole. So the net dipole, it pulls the water molecules together. So that makes it to be liquid. So that is exactly here. So water has a net dipole and it's a liquid at 25 degrees, while carbon dioxide has no net dipole. That is why you see the gases, because there is no net dipole, the gases are dispersed, and because water has a net dipole, the particles stick